So I just want to remind you from yesterday, the overall picture. Just to remind you, we are interested in differential equations of this form. Where x is irregular. And we learned that if x is a martingale or semi-martingale, we can do classical Ito theory. So right. So, I didn't get to fractional Brownian motion, which is the first example of a non-semi-martingale. So definition. O1D FEM is a centered continuous Gaussian process that satisfies the following properties. So the first property that it satisfies is stationary increments. FEM, let me write the H of T, where H is in 0 to 1. So it's going to depend on a parameter, which I might sometimes suppress the parameter just out of convenience. Stationary of increments, meaning that E of T plus K minus E of S plus K is equal in distribution to B of T minus B of S. So stationary increment. And it's also self-similar with parameter H. So that means BH of CT is equal to C to the H, BH of T. And just to normalize it, we have BH of 0 equals 0. And also BH of 1 squared is 1. So equal in distribution, same thing as up here. Equal in distribution. So this is actually not the standard way of defining fractional Brownian motion. People normally define it through its covariance. You can derive the covariance from this, and I'm going to do that shortly. But the reason why I'm doing that is basically, I think the reason why I'm defining it this way is it's defining it through its properties than just writing some arbitrary covariance. And also, I think this perspective shows how slight of a generalization this is to Brownian motion. Because if you just add one little extra assumption here that the increments are independent, then this gives you a Brownian motion here. So each variable is Gaussian, and each finite collections of variables is jointly Gaussian as well. Yeah, so continuous Gaussian process, and by Gaussian, I just mean you take any finite collection of times, then it's a joint normal. Yes, and I'm going to write down exactly what the covariance is here for 2 times, and then you can just use that to construct the covariance for all time, for all collections of times. So yeah, let's write down what the covariance is for this, just using these properties. And one really important thing about centered continuous Gaussian processes is that the covariance fully determines the process. So just really, yeah, really important fact. You know, for centered continuous Gaussian processes, R of ST, let's say Gaussian process X, determines X. Okay. So let's just try to figure out what the covariance is for FEM. We get expectation, B of T, B of S. I am going to suppress the H from now on. Implicit in these B's is an H. So this is not a standard Brownian motion. This is a fractional Brownian motion. And for a particular value of H, we will see 1/2 to recover Brownian motion. So this is expectation of 1/2 B squared of T of S. Okay. Just using polarization identity. So then this is equal to 1/2 expectation of, well, we can use the stationary of increments, and here I'm just assuming T is greater than or equal to S. We can use stationary of increments to get okay. Then we can use the self-similarity and get that this is T to the 2H B squared of 1 plus S to the 2H B squared of 1 minus T minus S to the 2H B squared of 1, which is just the covariance. Just the covariance. So usually the way fractional Brownian motion is defined is they say it's a Gaussian process with this covariance. But what I'm doing is just kind of going the backwards way. You'll define it this way and then show that it has these properties, but it's if and only if. Okay. Yes. There is, but it's the constructions I've seen are pretty complicated. So yeah, regular Brownian motion, you have Donskoy's theorem. For a fractional Brownian motion, I don't think that there's any easy thing I can say right now is you just take this limit or something like that, because you do have all of those correlations, which are kind of hard to deal with. Mm-hmm. 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 Uh-huh. Mm-hmm. There's actually quite a bit. So one thing actually is I'm gonna, in the proof that this is not a semi-martingale, we actually use Birkhoff's ergodic theorem, and I think you know that's maybe a way of understanding it. There's all this work by Kinshin about basically the correlations here decay as if you take the increment of this and then as you send t minus s an increment to infinity, the correlations decay to zero. So this work by Kinshin shows that it's actually ergodic. We can use the Birkhoff's ergodic theorem to so I'll show that's not a semi-martingale using that, but that's probably along the lines of what you're interested in is that the increments, they're not IAD, but we at least have some ergodic theory that we can do. So there's a lot of work done by Kinshin on this kind of results dealing with Gaussian processes. Mm-hmm. So the natural way, the way I understand it is that the stationary of increments and the self-similarity here, these are both properties that Brownian motion have. So if we just have that and then drop the independent increments, that's where I think it's a natural generalization, is that it satisfies all of the same properties of Brownian motion except for the independence of increments. So we're just introducing some correlation between them. So, mm-hmm. Uh-huh. Sure.
From a lot of things back, just say it's a Brownian, two-dimensional Brownian thing, where now you take a random matrix, which it bends things around so they use independence, you can analyze it, apply the transformation, over in some other linear. You seem to choose 3 times, 4 times, 7 times, to change the variable we do, we didn't. Right.
Yeah.
It's not, but at least there's a formula for it, right? Down the matrix, right?
Mm-hmm. So you can, yeah, you can for any finite collection of times. One thing that I don't know if this is directly related, but you can write fractional Brownian motion as an Ito integral. So you can represent it this way. And in general, you can represent Gaussian processes as Ito integrals, just for any Gaussian process, basically. So yeah, so that's maybe one thing that is maybe related. In terms of like doing some transformation to make this independent, maybe there exists something like that. It's probably pretty complicated, and I don't know it off the top of my head here, but yeah. Mm-hmm. 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 Mm-hmm.
Take a positive. You don't square root the matrix. The Hadamard square root. For some matrices, you can do it.
Mm-hmm.
Still get a positive. Other matrices, you can't. So individual means you take this thing where you take the 2 matrices per power.
Mm-hmm.
So you take smaller than 1 half. You can always take a larger power.
Mm-hmm.
smaller power. And there's a whole theory of infinitely divisible matrices.
Mhm.
It'd be good to see whether that matrix is infinitely divisible.
Yeah.
Take a finite number of one, but you take that matrix to whether it's divisible.
Uh-huh.
And I think there's some things where you got to take the ball and take these forward. Yes, in the theory about whether
Mhm. No, I haven't, but thank you. I appreciate that. Thank you. Mhm. Mhm. Yeah, it's not a semi-martingale. So it's a little bit complicated by what exactly we mean by an Ito integral here. But there's some representations like this. Okay. I can send them out. I can send them out later. Basically, the integrands are singular or can be pretty singular. Yeah. But yeah, so one thing was that. Mhm. Yeah. Right. Mhm. Right. Okay. So yeah, let me mention a couple more things about FBM. So for h equals 1/2, we recover regular Brownian motion. The h is the Hurst parameter named after Hurst. So the Hurst parameter. Right. So for h equals to 1/2, which is just the covariance for Brownian motion. So we recover standard Brownian motion, which is the independent increments. And then we can look at the correlation of the increments. So and you can write all of this out and you end up getting that. And the important point of this is not that it's just some formula, but we know the sign of this, which is greater than 0 for h greater than 1/2, equal to 0 for h equals 1/2, less than 0 for h less than 1/2. So the Hurst parameter, the h, tells you the correlation of the increments, how strongly the increments are correlated. As h goes to 1, we get basically a straight line. And as h goes to 0, I mean, it's not actually a process at h equals 0, but as h gets smaller and smaller, it becomes morely or strongly negatively correlated. So, and H equals 1/2 is like right in the middle. Right in the middle, that's the Brownian motion, totally uncorrelated increments. So, yeah, so let me say that this is not a semi-martingale unless H is equal to 1/2. So the point is, we introduce a little bit of correlation, and then we don't get, then we break the semi-martingale property. Mhm. Yes. Yeah. So actually, you can tell the roughness of the path. Yeah, right. The modulus of continuity or the roughness. So as H gets smaller and smaller, it becomes, very, very irregular. Because if you think about it, if the increments are very strongly negatively correlated, you go down and then you immediately go back up and it becomes a lot more correlated. Other things, for example, like the Hausdorff dimension of FBM is 2 minus H. So as you get H getting closer to 0, it's just going to look like just a space filling curve almost, right? And, basically as H gets smaller, it becomes extremely irregular. As H gets bigger, it becomes more regular. Exactly. And, that is actually why I'm introducing fractional Brownian motion within the context of rough paths. It's because it gives us an entire family of processes with varying regularities to study the different regimes. So the H equals 1/2 is the semi-martingale case where we can do all this Ito theory. H greater than 1/2, we can do Young theory. So we can do just standard Riemann-Stieltjes integration. H less than 1/2, we have to do the rough paths theory. So that's really the point, is this H equals 1/2, or equivalently in terms of P variation, P is equal to 2 is like right at the cutoff between the Young theory and the rough path theory. So let me just give a short proof. Or yes.
Study this people in advanced finance.
Mhm.
Yeah. Yes, that's before the.
So there's been, there's been a lot of people who have developed stochastic calculus with FPM, but the point is, in finance for H greater than 1/2, you can just do the classic Young theory that's been around for a while. It wasn't until there's okay, so there are other, there's maybe some other techniques people can use, but none of them have been nearly as successful as the rough paths theory, but definitely in finance. So one other thing people use fractional Brownian motion for is in rough volatility models, if you're interested in finance. So the actual volatility of a stock, Gatherall and some other people found that the volatility was roughly an FBM with H equals like 0.1, just from looking at real data. So that was like one approach that a lot of people in finance have taken, is trying to model the volatility. So the driving noise in the SDE is still would be like a Brownian, but it's with a random coefficient of the fractional Brownian motion. And people have studied other models like this as well. So yeah, let's. Well, this is for the volatility. So it's like the standard deviation has this negative correlation. So if the volatility went down before, it's going to go, they found that the volatility is going to go up later. But it doesn't necessarily translate to the correlation of the stock price, right? So I'm not a financial person, but. Uh-huh.
Next day,
So theorem. FBM is not a semi-martingale Yeah, so proof.
Those use processes are.
Mhm.
Visibility of a probably no, as far as I know, there's no real connection. There's many things that seem to be riding down parallel roads.
Mhm.
Nobody's figured out a way to take a theorem on one side and apply it on the other.
So so for theorem, FBM is not a semi-martingale unless h equals 1/2. We're going to look at the quadratic variation. And if you recall from before, semi-martingale, or at least martingale has a non-trivial quadratic variation. So have non-trivial quadratic variation. And a semi-martingale, we're just saying is a martingale plus some finite variation process. So, if the quadratic variation is 0, then it's just a finite variation process. But if it doesn't have finite variation, then it's not a semi-martingale, right? So what we can do is we can look at a variational sum. So we can look at the variational sum B of n e TK, actually, yeah, let me just use uniform here. So B of a plus 1 over n minus B of k over n to the p. And then this is just a partition of the interval 0, 1. Yep. So then from this, we can use the self-similarity properties. We end up with this is equal to, in distribution, to n to the minus HP, B of just k plus 1 minus B of k. Okay. So yeah, so this is equal to that. And then what we can do is we can multiply this by n to the HP minus 1, and then we can apply Birkhoff's ergodic theorem. So we have that, say like y np is equal to n to the HP minus 1, b np, which is equal to 1 over n. Right. So the sequence is stationary because it has stationary, the process has stationary increments. The correlation decays to 0, or the autocorrelation of the increment process called fractional Gaussian noise decays to 0. So some classical theory condition shows that this is actually ergodic or even mixing. So this guy here converges almost surely, and L1 to to that. All right, work off. Mm-hmm. Oh, the FEM? Yeah, the FEM can be extended to the, is defined on the entire real line. Here, I'm just taking a partition of 0, 1, and then you can relate that to the FEM on the entire real line through the self-similarity. Right. So, well, I'm saying like equal in distribution to something over the entire line, right? So the FEM exists for the entire positive real line. I'm just looking at 0, 1 right now. Yeah, this is true for all P. Yep. Mhm. So then, what does this say? Is that so what does this say is that this implies that the limit in probability of this when P is just equal to this expectation here. Okay. And then what we can do is this shows additionally that the limit in probability of the variational sum is equal to 0 for pH greater than 1 and infinity for pH less than 1, right? Just taking a look at the variational sum. Then from there, if H is greater than 1/2, choose P less than 2, so pH is greater than 1. Okay. And then this implies that the quadratic variation is equal to 0. Okay. So P is less than 2, and then we end up with 0. So P being even more, we end up with 0 quadratic variation. And then if H is less than, or if H is less than 1/2, choose P greater than 2. So pH is less than 1, which implies that the quadratic variation is infinite. So the quadratic variation of FEM is 0 if H is greater than 1/2. It's just going to be T for H equals 1/2 for Brownian motion. It's going to be infinite for H less than 1/2. So every semi-martingale has a non-trivial. Every martingale has a non-trivial quadratic variation, and we can also show that FEM does not have bounded variation, so it can't just be a strictly, a semi-martingale with no martingale term either. Okay. All right. So FEM is, just the point I'm trying to make here is that for H equals 1/2, we have a semi-martingale or even a martingale. You perturb H even by the smallest amount of epsilon, and you break that. You're out of the Ito theory. And one more important thing about FEM is the Holder continuity of it. So So FVM is almost surely alpha holder for all alpha less than H. Okay. So proof of this is just Kolmogorov. So because it's Gaussian, we have that, just remember, we have that, right? So then we can look at the 2n. And because the increment's Gaussian, we just get some constant depending on n. The 2hn. So then Kolmogorov gives that he is almost surely alpha holder for alpha less than 2hn minus 1 divided by 2n. And then you can choose n large enough to get any alpha less than h. Okay. So it is polar continuous up to h minus. So I'm just saying if you take a like a t minus s, well, okay, so you're holder continuous on fixed interval is what that's what you're asking. Yeah. You're locally holder continuous. Yeah. Sure. I mean, this is just Kolmogorov, right? But yeah, okay. Okay. So one point I want to make about holder continuity and p variation. So rough path theory can be done both in terms of p variation and holder continuity. In this class, I'm mostly going to stick to the holder continuous case, but just out of convenience. But there is a relationship between the two. P variation is slightly more general because you can allow jumps. That's the really important point. So just a couple facts just to remind you. It's, pretty easy to see that if F is, let's say, I'm going to write in C alpha. So C alpha is just, all G. So that way soup over T not equal to S, G of T minus G of S. T minus S to the alpha. If F is in there, this implies that F is in C to the 1 over P variation, which is the all functions with finite 1 over P variation. We have a sort of converse of this. And one of the converse is if F is continuous, F is in C P variation, then there's a reparameterization. of time, say sigma from, just working on some time interval. So f of sigma of t is c to the 1 over p holder. And this is the holder space. So yes, so the that should be a 1 over alpha. Sorry. Should be in so if you're alpha holder, then you have finite 1 over alpha variation. And then if you have finite p variation, you can reparameterize, and if you're continuous, to be holder as well. Interestingly enough, for Gaussian processes that have finite p variation, there's a deterministic reparameterization so that you're almost surely holder, which is actually a very useful, not super well-known fact. All right, so let's get started on Young integration. Yeah, so p variation can include jump processes where a alpha holder is continuous, right?
I remember seeing a week over, so you can balance the movement way, then you're guaranteed that your process can only have time jump.
Sure. Yep. Yep. Mm-hmm. That's right. Mm-hmm. Mm-hmm. Yep, exactly. That's right. That's totally true. Mm-hmm. Exactly, right. Exactly. Yep. So let's get to Young integration now. And Young integration is the 0th order of rough integration. Okay. So, and Young integration is very classical theory. Young published his paper in 1936, but it seemed like it didn't really gain any traction until, or maybe it did, but it seemed like it wasn't super well known until rough paths came out, and then it's become a very, very well cited by now. So theorem by Young in 1936. Yes. So yeah, it's exactly the same Young, and Young's inequality, and actually there's some inequalities in here that look very similar to Young's inequality. Okay. So so let F be alpha holder, G be beta holder. Let Pn be a sequence of partitions with Pn mesh size going to 0. Then exists. Or as a Riemann-Stolzschius integral. So this very classical theory says that if, F and C alpha, G and C beta, with alpha plus beta greater than 1, very crucial. Then this exists as a Riemann-Stieltjes integral. So let me just say how this applies for us. So we're interested in defining f of x of s, dx of s, and say f is C1 with bounded derivative. Then, so as a corollary, this integral exists as a Riemann-Stieltjes integral if x is in C alpha, alpha greater than 1/2. So as a corollary, but the point is, for example, for FPM is C alpha. So if H is greater than 1/2, you can just do Young integration here. I don't have too much time. I was going to offer a half proof of this, or at least proof of this using dyadic partitions. But the main point here is that the way you want to think of it is if G is not of bounded variation, you can kind of borrow variation from F, right? That's the way you're thinking about it is F and G, they aren't necessarily, all of the regularity doesn't have to be concentrated on G. It can be kind of evenly split between the two. Well, I'll show you basically at least one proof using dyadic partitions, and you can just get some bounds. You can do some, you have a geometric sum with an alpha plus beta minus 1, which converges for that. Mm-hmm. Mm-hmm. Exactly. That's exactly right. And yes, so it's symmetric. Yep, that's right. And this is the 0th order of rough integration. So here, this includes for all processes for alpha greater than 1/2. And then the first order is going to be processes that are alpha holder between 1/3 and 1/2. And then, you can keep on going lower regularity, but you're going to have to include extra terms, basically, which are these iterated integrals. Yeah, so anything else I wanted to mention on this? The next time we meet, I'll probably just prove this for at least dyadics, which I think is, it's definitely a good thing to see. And then after that, I'll give a brief computation that shows that you have to define iterated integrals in order to define this. So a rough integral is basically a Riemann-Stieltjes integral plus some like regularization terms, some kind of terms that are like correcting the divergence, basically. So any questions on this? Oh. Yes, go ahead.
So here, if it's about duration,
Mhm.
think about the graphic equation.
Yes.
So why this
Well, if you remember from the beginning, we're expecting y to be a function of x. So if y is, if we have something like that over there, if f is a C1 bounded derivative function of x, then we expect it to have the same regularity as X. And we can show this, we can show everything works, and later on I'm gonna show that everything works. But yeah, you expect the solution to have the same Holder continuity, the same regularity as the driving signal. Because it's a function of the driving signal. We really want it to be a function of the driving signal. I mean, the point of the SDE is we're looking for something that is a function. So, I mean, the way we set things up, we can prove that it has the same Holder regularity, and we could show that everything exists, and we show that it all works out and it's all true. But I mean, we would change the theory if that wasn't the case, because we want the solution to depend on the noise, right? So, I mean, that's sort of the point of developing this theory, is so that way the solution is a function of the noise, right? Yeah, you can do things like that. You can generalize things like that. And then in general, we're going to get to what are called controlled rough paths, which are basically the class of integrands that we can handle, which include solutions under certain assumptions and things like that. Yeah. One last point I do want to make with this Young theory is this Young theory, is very classical. And again, there is absolutely nothing to do with stochastic processes here, right? So this is just a statement about Riemann-Stolz's integration. And going forward, kind of from this point on, I'm going to talk about stochastic processes occasionally, but most stochastic process theory is going to be kind of put in the background a little bit, because everything here is done completely pathwise. So there is no, like, from this point on, there's no probability theory anymore. Exactly, right? That's the point of our paths, is we want to get rid of all the probability basically. I mean, there's times when it comes up, there's like stochastic sewing lemma and all sorts of things where it interacts with probability, but a priori rough paths is not random. Yes. Yes. Mm-hmm. Yes. Mm-hmm. 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 Mm-hmm.
But what is the difference if I say that you agree something like wrong motion, right?
Mm-hmm. Mm-hmm.
That you put it down as a correlation.
Mm-hmm.
It is kind of factor on which thing. So it was, I mean, whatever makes sense.
Sure.
What they don't want is the system.
The honest answer, like, I can give, examples where it models a lot of things. I mean, the Hertz phenomenon is important, but we can go to more general Gaussian processes. The fractional Brownian motion from a modeling standpoint. If you don't like that, we can go to bifractional Brownian motion. We can go to more general Gaussian processes. We can go to a lot of different things. Rough paths handles all of them. So, I can send you some. Mhm. 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 Mhm.
Showing that the H number, they look at the H number, that's good. If you have too many parameters, they have your portfolio and the other guys portfolio,
Like simple things. I don't know. The number in the future
Mhm.
is very elegant.
Sure.
You wish that in the 60s, 70s. The one that they elaborate the most.
Mhm.
The skill of the exchange of the models, the primary value, and then you want to say, okay, I'm not going to allow the contribution value.
Mhm.
And you can really keep its calculation for making stereo.
Mhm.
Stereo is more like a spectrum. That's it.
Mhm. Well, thank you.